speak about. Yeah, I got it. Yeah. Yeah.
Very good.
So I'm going to talk about the topological recursion. Topological recursion. And yeah, generalized Hurwitz numbers, double Hurwitz numbers. So what is topological recursion? So the talk in general, I'll speak about topological recursion and its connection with integrability and enumerative combinatorics and maybe some Gromov-Witten invariants, but I think no. So what is topological recursion? This is a like universal procedure which appears in many. Do you? So the
Yes,
I hope you hear me. It appears in many different areas of mathematics. So I mean, what does it mean? That very many different enumerative problems governed by this topological recursion procedure. It's like universal. Okay, I now want to present these problems, but without any definitions, so just words. So like Hurwitz numbers, enumeration of maps, matrix models, some invariants of nodes, and Gromov-Witten invariants of some particular spaces. So all these problems, enumerative problems, governed by this procedure of topological recursion, and it means that if we like count something and construct some generating series in a clever way, and construct this, roughly speaking, this generating series for the numbers we are interested in, satisfies one and the same recursion procedure with one and the same expression for the recursion. So this recursion is very universal, and so I'm going to like define this topological recursion, and then maybe I will in particular present some examples concerning these Hurwitz numbers and generalized Hurwitz numbers. And so what is topological recursion? What is a topological recursion? So again, it's a recursive procedure. As initial data, it has the following data. So we have sigma is a Riemann surface, so it's compact-oriented two-dimensional surface. Compact-oriented two-dimensional surface. And we have two meromorphic functions on sigma, so x and y. Meromorphic functions on sigma, such that zeros of let me. So I want to the following conditions. So the zeros of dx are simple. Zeros of dx are simple, and zeros of dy are away from zeros of dx. So zeros of dy do not coincide with zeros of dx. Zeros of dx. And also I need some which calls it calls Bergman kernel, some B of Z1, Z2. Okay, maybe yeah. B of Z1, Z2. It's a symmetric to form on sigma square, so it's a symmetric to form on sigma times sigma. So it's a like a one form in each variable on sigma. In variable z1, it's a one form on the first copy of sigma. In variable z2, it's one form on the second copy of sigma. And so you may think about this B. So in all today and in most cases, when in like most examples, B, or you could take for B the following expression is dz1 dz2 over z1 minus z2 squared. So in general, it should be some to form with double pole on the diagonal z1 is equal to z2 and symmetric, and also some conditions about the intersection of this B with A periods on sigma. But nevertheless, you can take B, you can think about B as this expression. And so I said that sigma is just any two-dimensional surface, but in fact, today sigma always be a CP1, so it's just a Geno-zero curve. And so for me, in fact, sigma is CP1. And yeah. And so this procedure produce invariants of this topological recursion, say differential of this topological recursion. So TR produces omega gn of z1, z2, etc. Zn. It's meromorphic forms on the nth copy of sigma. So it's a n form meromorphic n form on sigma times sigma n. So again, it's a in each variable, it's a meromorphic one form on the corresponding copy of sigma. And so topological recursion starts from omega 0, 1 and omega 0, 2, and produces all higher omega gns. So, and this recursion relations looks like follows. So omega gn of z1, etc. zn is equal to some expression of omega g prime and prime with g prime with like 2g prime minus 2 plus n prime less than 2g minus 2 plus n. So it's a recursion on Euler characteristic of, say, Euler characteristic of this gn. So on this number 2g minus 2 plus n. So the recursion in this number. I do not want to write down the relations of recursion itself, so this expression. because they are not important for the talk, and I'm afraid that if I write them down, so that they will not increase the understanding of what is going on. So there is some explicit expression how you write omega gn in terms of omega g prime and prime with less g prime and prime, in fact, with these relations. And this expression is very universal, as I said. Many different enumerative problems governed by this topological recursion. So again, what does it mean? It means that if you have some numbers which you are going to count, then you like compose them into some generating series in a clever way, and they, after some substitution of variables, this generating series is this. So, and if after some changes of variables, this generating series satisfies this recursion, then it means I say that this topological, this enumerative problem satisfies topological recursion. So why it is interesting and important for us? So it was like a definition of topological recursion.
Sorry. However, I suppose that this relation of higher generating functions and the lowest one has some geometric nature, and is it possible to comment?
Yeah. So it it has a geometric nature, a bit formally, but nevertheless. So you may think about these relations as follows. But so let me draw a picture, and then I'll comment. A picture is follows. So if you have surface with boundaries, say with with n boundaries, yes, genus G with n boundaries, so this is boundaries, yeah. So here, so it's genus G and n boundaries, G genus n boundaries. So here we have like 4 boundaries, and the genus is equal to 3. Then we can cut this surface somewhere, and there are 2 possibilities. Either we can cut off a pair of pens from the surface, and in the end we obtain either the other part of the surface stay connected, or will be disconnected, and so we cut off a pair of pens. Some in a question, a pair of pens, I mean we cut here in this red line. So we obtain I call it a pair of pens, so it's like a pens, and either the other part is connected like this, Yes. Or disconnected, then we have some like some overall cases where we get disconnected. Other part of the surface will be disconnected, and so this is like an informal way to see the recursive relations. But in fact, so I obtain here something like this. Yeah. So here we have G1 and G2 that will give genus G. So, but in fact, this picture very informal and only like so I mean it. You can think about it as a just informal picture, and it will not produce some geometrical meaning of the recursion, of the topological recursion. But the recursive relations, yeah, they are very much looks like this cutting off a pair of pens.
We are still talking about meromorphic n forms.
Yeah. So
of the
but
singularity
here
is
just a very informal picture. So a very informal picture. So you
okay.
have a meromorphic form, but you're instead of meromorphic form, you picture this surface with boundaries. But this picture, yeah, exists. So yeah, in fact, later I will present another definition of topological recursion, which is a like equivalent definition of topological recursion without this expression, without this I mean expression that is in fact uses when you are proving that some numbers, some enumerative problem satisfies topological recursion. And in fact, if you see that someone says that, oh, I proved topological recursion, that it's with like 99% that he means that he proved this equivalent definition of topological recursion. But I'll give it a bit later. And now, yeah, maybe some more questions.
But am I right that the relation between different functions omega, it is something like the axiomatization of the correlation function of a topological field theory, quantum topological field theory?
So if no. So it connects with cohomological field theories, but it's like it's a relation of different nature, I would say.
Okay.
So yeah, really, what in my talk today, what is the what we're interested in, what examples of topological recursion we're interested in. In fact, let me start with so it's a seminar in integrable systems and related topics. Let me start with the Kp tau function of hypergeometric type. Kp tau function of hypergeometric Rec-type. So what is it? Let Z is the following series. So it's 1 plus sum over n and sum over all partitions of n. So lambda is a partition of n. Then products over all boxes of this of Young diagram corresponding to this partition lambda, some function phi of h j minus I. So this means this means that lambda is a partition of n. So it's some Young diagram. And this I and j is a coordinate on this Young diagram. So j minus a is a content of this Young diagram. So here we have zeros and ones, and here minus ones and twos, and etc. This is this j minus I. So this is some product where and phi here is in fact any, so phi of theta is just any formal power series started from 1. So 1 plus like theta k z to the power k. So it's any formal power series, and then I want to here sure functions of this p variables times sure function of q variables.
What do you mean phi of theta? Phi of z?
Oh yeah. Phi of z. Yeah. Yes. So and yes, and s lambda is a sure function. S lambda is a sure function. Yes. So and this is z. So this is z. And in fact, this series has infinitely many summands with h in the with negative powers of h in the denominator. But when we take logarithm of z, let's write f is h squared logarithm of z, then this f is a formal. So it doesn't have negative powers of h bar. I mean h bar. Yeah. So it's a formal series in h bar, and in fact this f. So this z is a tau function of kp. So kp hierarchy, and this f satisfied this it's called hkp hierarchy. So this is theorem, I think, Sherbin, and maybe like Goulden-Jackson later, but in Goulden-Jackson formulated it in this form, which more or less which I formulated this, that Z is a tau function of HKP hierarchy in p variables in p variables. So this F satisfies hierarchy. So the first like few equations of this hierarchy are follows. So F satisfies F22 and so F23 so I mean here indices is a derivative with respect to like 1 3 means that it's derivative with respect to p1 and p3 and etc. Yes, so and
but could you say just a few words how the HKP hierarchy is related with the original one?
So you have to insert the parameter h bar in relations and so you see in this form you just have to add this h bar here. I mean in these variables pi's which are these pi's connected with the usual t variables of KP hierarchy like tk is equal to pk over k, I think. Yeah, but yes,
what are the sorry, the indices are what do they correspond? F22, F13, what are these indices?
So F22 is just df over
derivatives.
d. Yeah.
Over Z1, no, P1.
P in P variables. Yeah.
In P variable, PI, right. Okay, fine.
Yes. So. And how we obtain this integrable system, starting from some problems of counting some numbers. It's another theorem. I would say a Gromov. That if let me write follow. So if phi is equal to e to the power some polynomial. Okay. Yeah, so it's an exponent of some polynomial. Then this f, then f is a generating series for double Hurwitz numbers. This double Hurwitz numbers yeah. These double Hurwitz numbers has a combinatorial definition in terms of counting permutation, just counting permutation of with some conditions. But maybe I'll give another geometric definition of this double Hurwitz numbers. So what generating series? If F is a generating series for double Hurwitz numbers, following generating series. So F is equal to sum over all G, H to G minus 2 plus N, H, this H bar, and this H for Hurwitz number, G mu nu, Q, P, mu 1, etc. P mu N, and Q nu 1, etc. Q nu K. So this is Hurwitz numbers, and this mu is a partition, and mu1, etc., mu_n are parts of this partition. So mu is equal to mu1, etc., mu_n, and the nu is equal to nu1, etc., nu k. And so this, yeah. And what is Hurwitz number, double Hurwitz number? It's Hg mu nu. Hg mu nu is a number of equivalent class isomorphism classes of ramified coverings. So it's isomorphism classes of ramified coverings of a sphere of S2 by Riemann surface of genus G, some Riemann surfaces of genus G with some with some conditions on ramification profile. Conditions are follow. So we have two with ramification profile. With following ramification profile, yeah, with following ramification profile. We have 2 points with ramification which are corresponds to these partitions mu and nu, and all other ramification points are simple. So 2 points of with pre-images, 2 ramification points with pre-images mu1, etc., mu_n, and mu1, etc., nu k, and all other ramification points are simple. So so you have here some S genus G, and here you have a sphere CP1, and so you have 2 points, two non-simple ramification points, and with profile over them this mu1, etc., mu_n, and new 1, etc., new k. And all other ramification points are simple, just and the number of isomorphism classes of such coverings is a double Hurwitz number. So again, what we have by now, we have some I'm afraid my video. Do you hear me?
Yes, yes.
Okay.
But I'm afraid my video maybe. Okay, I'll try to reconnect.
Back at CP1.
Okay, it works.
Yeah. Boris, you have an infinite series. There is no question.
So
any question of convergence? You have an infinite series there above, but it's a formally series.
Yeah, it's a formal. No, it's a formal power series. Yeah.
Okay.
It's a formal power series. Yeah. So yeah. Okay, I'll try to turn on my video again. So what we have by now? We have some combinatorial. Yeah, we have some combinatorial problem, which I defined in terms of this ramified coverings. Combinatorial problem. And which are from which we obtain some this omega gn. I didn't say how, but we can obtain this omega gns. Say maybe omega gns.
Mm-hmm.
And also I will say in a few minutes, from this combinatorial problem we can construct this initial data for the topological recursion. So this sigma x, y, and b. Let me say Hurwitz numbers, and this is the initial data for topological recursion. And so the theorem which I also will present says that in very general situation, so we have we prove very general for the very general families of data. We prove this that these omega gns, which are constructed from combinatorial problems, satisfy topological recursion. So here is some theorem which I will present. And but in fact, as I said, we start in fact not with a combinatorial problem, but with this series, which is a tau function of which you may think as a tau function of KP hierarchy. So here we have like KP tau function. So this is the picture of what we have here. And so maybe I want to say a few words why it's interesting in general. So my village. Okay. So what is this theorem? For different types of this. So as I said here, this theorem of Okounkov for the particular choice of this phi function, and so for different types of phi, and for different choices, different choices of phi, and in fact, this y function, which is this y function, we obtain different types of different enumerative problems. We obtain different enumerative problems. So different types of Hurwitz numbers, enumeration of maps, and others. So the point is that this family of KP tau functions, which I described, covers many of enumerative problems, and all these enumerative problems, in fact, satisfy topological recursion. So in how it looks like, if we have this h g mu nu, this Hurwitz numbers, so h g mu nu Hurwitz numbers, then let me compose them into a little bit different generating series, again formal generating series. So let omega gn of x1 etc xn is the following guy. Sum over all partitions h g mu nu x1 to the power mu I mu 1 xn to the power mu n. So here I more or less forget about this second new partition, and omega gn, which are of z, which will be this differential for topological recursion procedure, are follows. So it's omega gn over x variables with the substitution xy is equal to x of zi. Sorry. dz1 etc dzn. So this this change of variables x of zy corresponds to this function x on the spectral curve. So we have again, if we have our initial data for topological recursion, we have the sigma x and y. We have some affine coordinate z on sigma. So we have function x of z and y of z, and this y of z is here in the, so that it correspond to the problem itself, and this x of z is this change of variables. And then we have a theorem of me and like 3 more people. Donin, Barkovsky, Petya, Maxim Kazaryan, and Sergei Shadrin. That for the two families of this families of phi and y functions, of phi and y functions, omega gns, this omega gn of z1 etc zn obtained from F. So what does it mean? Okay, I satisfy. I will finish and then comment. Satisfy topological recursion with change of variables x of z is equal to z over phi of y of z. So what does it mean again? We have this kp tau function in terms of Schur functions, this formal generating series, this number is this one, in terms of p variables, and for some fixed phi and y, we have in for general phi and y, this Taylor coefficients I say does not hold. So they're not really Hurwitz numbers. We just some numbers, some generalized what we call Hurwitz numbers, some Taylor coefficients of this series F in terms of p and q variables. So we take these numbers and build this W, this new generating series for these numbers just with different variables, and then build these omega gns. And the theorem is that these omega gns satisfy a topological recursion procedure. So okay, some questions, more questions.
Buri, I have usually questions of general nature. So could the topological recursion some relations on some coefficients of some object which you construct from the tau function, could they be expressed equivalently by some equation on the tau function? Some equation, some differential equation of some functional equation on the tau function of the KP hierarchy.
So the recursion, the recursion is, there are some so-called in many problems, in many enumerative problems, there are so-called cut and join equations or Virasoro equations for this. So for this where it is, for this f function, which in fact more or less tau function, yes, or for z function itself, but this functional relations or differential equations are weaker than recursion itself. So the topological recursion relations are stronger. So if we have this cut and join or Virasoro equations, we should prove. So we have them, but again, we should prove this topological recursion relation. But there are some correspondence with it, yeah, some connections. But I would say that so yeah, I would say that these equations, cut and join or Virasoro, they have they weaker and they have less information than logical recursion.
Okay, thank you.
Okay, so what about
Boris,
yeah?
Suppose I have a problem that is not integrable, but I don't know it. I have a hierarchy of equations that are a little different than the KP, and I don't know if the problem is integrable. Where would I fail in this construction of tau functions and the theorem that you proved? Should I? Yeah. Where would I find that the recursion relation doesn't work and the problem is not integrable?
Yeah. So the point is that it's not like if and only if. Yeah. So the first answer is that our theorem is not if and only if. Of course, there are examples of topological recursion which are not coming from this family of tau function. Just this family of tau function is very wide and it's cover very many different enumerative problems. And the second answer, so the second answer that it's a difficult question. So I mean,
so you mean if it works?
I mean, maybe. I mean, yeah. I mean, maybe what I'm going to do now, it's an equivalent definition of this topological recursion. It's like how we prove it, and then you will see really what conditions we want from these omega gens, from these meromorphic differentials.
Okay. Let's work.
Yeah. So, okay, yeah. Equivalent definition, in fact. Definition of Jar. It's in fact a theorem, theorem of Boro and Shadrin, 2017, that family of meromorphic differentials, omega gens on spectral curve on the this initial data sigma x, y, and b usually calls spectral curve. So on the spectral curve sigma, so it's initial data sigma x, y, and this b differential b family satisfies TR if and only if the following conditions are satisfied. So omega gens are symmetric, in z variables, that, so again, it's a meromorphic differential. So the poles only in the zeros of dx. So poles of omega gens only in zeros of dx. And some combinations of these omegas. So the following expression, omega gn of 1 plus omega gn of sigma I of z1, z2, etc. zn. So this sum of two omegas, what is sigma I? So let let me let p1 etc. pn, it's a zeros of dx. Then and they are all simple. So one of the conditions of topological recursion above was that these zeros of dx are simple, and this sigma I is a holomorphic involution which changes branches of double cover. So we have a double cover x of z over z because in the neighborhood of each zero p1 etc. pn. So in the neighborhood of p1, say x of z is a double cover, and we have two branches of this x of z, and this sigma 1 changes this branch. So if we have like x of z is equal to z squared, then sigma of z near this near zero is just z to the minus z. So it's holomorphic involution, and so sigma I is a holomorphic involution in pi, and the condition is that this combination, this expression, this expression is holomorphic in the neighborhood of this of pi for any I. Is holomorphic in the neighborhood of pi for any I. Okay, and the last condition, that one more expression, also holomorphic in the neighborhood of pi for each I. So the following expression, omega g. So in fact, this n plus 1. In fact, this expression is very much looks like to the expression of recursion itself, but does not coincide with the recursion. But you see here this, if you remember these pictures, which Dima asked to write down this omega g minus 1 and plus 1, and when we cut this pair of pens and obtain connected surface, and this sum of when we obtain two disconnected surfaces. So thank you, Dima. Yeah. And here, product of two omegas. So times, I mean, the sum of product of omega g2 G plus 1 sigma I C1, not bad. Okay, times omega G2 sigma I Z1 ZJ. And again, holomorphic yeah. Again, is holomorphic in the neighborhood of pi for any I. So what's written here, again, sigma of I, this holomorphic involution, and here I sum overall partition of G1 plus G2 is equal to G, and E and G is a set from 2 to n, and when I write Z with index with a set index, I mean that it's just a tuple of variables with indices from this set, so as usual, more or less, yeah. And so what means what this conditions mean? Maybe I could zoom out a bit. Yeah. So in fact, these conditions mean that we have certain symmetric meromorphic differential with prescribed poles, and moreover, we know the behavior of these omega gns near these poles, and therefore we can reconstruct this omega gn on the whole curve because of we know how they behave near all their poles. And in fact, you see that this second condition means that says that something is golomorphic. So you could write it like that. The polar part of this form is equal to 0, and then if we if you see a little bit more to this sum, you see that here here we have summands where G1 is equal to 0 or G2 is equal to 0, and G1 is equal to G, and then also one of I or J capital is empty, so you have summands omega Gn, I mean, here in this, and if you just move them to the different side of something like 0, you obtain this recursion relation, which I didn't write down. But again, this equivalent, in order to prove topological recursion, you have to somehow understand the behavior, understand this omega Gn, so prove that these omega Gn's are some rational functions with prescribed poles, and these two their behavior near ramification points. And in fact, that's how it works. How it works, we just prove this. Okay, some questions.
This type of relation resembles a lot to the business of deformation quantization. So the first idea which came to me is the relation with homotopy Frobenius algebras. Do you have you heard something about?
So there is a close relations to the so to the Dubrovin-Frobenius manifolds.
Yes, but to the homotopy Frobenius manifold.
That's
With highest operations, with highest symmetric operations, like
this I don't know. So the what I more or less know is the connection with with the cohomology field theories and the given Tal-Telemann reconstruction of cohomology field theory from the topological part of this cohomology field theory, and so there is a in fact this scheme you could what we did here, we like for starting from this KP tau function, we obtained some universal proof of the topological recursion, and here you have this given Tal-Telemann theory, and this given Tal-Telemann reconstruction immediately give some ELSV, so give some expression of these combinatorial numbers in terms of some intersection classes on the moduli spaces of genus G curves within mark point. So this given Tal-Telemann connects to the intersection theory on MGN bar. But I think it's and it's a very interesting. About homotopy Frobenius algebra, I don't know.
Okay. If I may ask some question, have you finished, Boris? You have more to.
What about Dima? What about time? So I can say a few words more about proof, or can stop here about methods of proofs.
Okay. Let me ask something. If you roll it down a little bit, please. When you state the problem here, a combinatorial problem. No, near the end, where you are now. You start with a combinatorial problem, but then you use as an example the KP, the tau functions from KP. I presume is Kadovchev-Petiashvili.
Yes, sure.
It is. So it seems to me.
Sorry.
Yes, KP hierarchy, the Kadovchev-Petiashvili.
KP.
And you have a tau function, which was a long time ago a popular way to study integrable PDEs through the tau function approach. When we don't have a tau function, it seemed to me that your combinatorics was very general, but then you connected it to the KP tau functions. Is that a special case, or do you really need such a structure of tau functions?
In fact, the answer, so both is right. So at first is somehow a special case which are in fact very general, and second, we really use this representation in terms of a Schur function in our proof, because of so this, what does it mean? This tau function, this Schur function, it means that we have some point in semi-infinite Grossmanian. So the tau function as a plane of in a semi-infinite Grossmanian, and we have some so-called boson fermion correspondence, and we rewrite this series using vertex operator, and in this formalism allows us to prove these conditions which are below. Yeah. So in fact, we use this representation a lot.
Right. So if I take another hierarchy, say the KDV, Korteweg-de Vries, or another, they must have tau functions to work with, huh? To apply your
sorry, could you please repeat? The internet connection
I'm saying,
poor.
Let's take another hierarchy, Korteweg-de Vries equations, or different than KP. I should first find a tau function approach to the problem in order to find your recursion operators. Can I do this for another example besides the KP?
So there are examples of TODA and also KDV also, and also some reduction of KP. That's what I know. And the connected interesting question is how, I mean, how, so we have like a point in this some particular tau function, and the open natural questions, and how many different tau functions of TP we obtain in such a way. And I mean, if we as I mentioned, this vertex operator, we have this we have a representation of this Z in terms of vertex operators, and we can change a little this vertex operator. And the question is what tau functions we can obtain in such a way. Yeah. And also your question also exists. Yeah.
But it is very interesting. My understanding of the subject converges, but I think we can discuss the proof in private communication.
Yeah. The meromorphicity also. You see, every time I look at integrable systems and PD and ODs and PDs, I always come up with the property of meromorphic functions that have there has to be no logarithms, no any other kind of singularity, right? We must have meromorphic functions and to be able to work with, right? These are very crucial.
Yeah. So you have you can mild. In fact, you can a little bit mild the assumption of this spectral curve. So this what I said, this condition that the zeros of dx should be simple, you could mild it, and in fact you can take not global meromorphic function, but like some
locally
locally near these points meromorphic function, but nevertheless, yeah.
Right, very interesting. Okay, thank you very much.
Thank you. Thank you for the question.
Are there any questions? Other questions
from the audience?
Okay. Boris, thank you very much.
Yeah, thank you.
Thank you. See you next time.
Okay.
Yeah, see you.
Bye-bye.
Bye-bye.
Bye-bye.